Okay, so we would like to go over the review problems from Calc 1 and Calc 2, and also the new problems from Calc 3 for week 3. So let's start with the review problems. So the first one is to take the derivative of sine to the third of x. It's actually a good idea to think of this as sine of x all raised to the third power. And the chain rule tells us that we should treat the inner function as pretty much a new variable. So think of this as y to the third and ask yourselves, what is the derivative of y to the third? And the answer is 3y squared. So we're going to write 3 sine of x all squared. That was our y. And we're supposed to multiply by the derivative of what we designated as y, meaning the derivative of sine x. So that will give us cosine x. So if we want to write it a little better, that will look like 3 sine square of x times cosine x. Okay, let's go to the next problem. The next problem is the derivative of 2 to the cosine x. So here, we are going again to use the chain rule. Let's think of the quantity cosine x as y and ask ourselves, what is the derivative of 2 to the y? And the answer is 2 to the y ln 2. So this will be 2, I'm not writing y, I'm writing cosine x instead, cosine x times ln 2. And now I want to multiply by the derivative of what I designated as y, meaning the derivative of cosine x, which is negative sine x. The next thing that we have is an integral. So the integral from 1 to 2 of 1 over x plus 1 dx. Here, even though it's very simple to write the antiderivative, let's just make it as simple as possible by doing a substitution. U is equal to x plus 1 and du is equal to dx. And this will be 1 over u times du. And now you have to remember that when you do a substitution for the definite integral, you apply the substitution to the endpoints. What do I mean by this? Let's write down the general formula. So if this goes from a to b and you apply the substitution, u is equal to g of x, resulting in du is equal to g prime of x dx, then this will give you the integral from a to b of f of u du. I'm sorry, that's the point I want to make. It is that it's going to be the integral from g of a to g of b. Okay, not from a to b, f of u du. So in other words, you need to apply the substitution to the endpoint, which means that in our current situation, we need to apply the substitution x plus 1 to 1 and 2, which will give us 2 and 3. And the antiderivative of 1 over u is ln of absolute value of u. We can skip the absolute value because this is a positive range. And we're going to go from 2 to 3, resulting to ln of 3 minus ln of 2. You know that this ln of 3 halves, but we can leave it like that. And that's the end of the story. And the last review problem is the integral from 0 to 1 of e to the 3x dx. And here again, we can do a substitution. U is equal to 3x, du is equal to 3 dx. And that's the same thing as saying 1/3 du is equal to dx, which will give us what? It will give us e to the u. Dx is 1/3 du. We have our integral, and again, we're supposed to apply the substitution to the endpoints. That will go from 0 to 3. And this, of course, will give us 1/3 times e to the third minus e to the 0. Of course, we all know that e to the 0 is the same thing as 1. So this is 1/3 e to the third minus 1. Okay, it's a good idea to go over these problems yourselves by pausing the video and try to do them even after you have seen the solution once. And now I think it's time to go to the main dish. So that was the appetizer. The main dish is, of course, problems on equations of lines and planes. And the first problem is the equation of the line. So find an equation. The problem says the equation. It's much more correct to say an equation for the line between 1, 2, -1, and 3, 1, 3. We know that the basic data for the equation of a line is a point on the line and a parallel vector to the line. So they look like this, right? But we have a case, and it's very useful to know this case where we're given 2 points. So let's say that we have x0, y0, z0, and x1, y1, z1. And here there is a formula that is pretty much ready to go. And the formula is r of t, or L of t, whatever you want to denote it by. It's the vectorization. When I say vectorization, I mean, so 1 minus t first times the vectorization of the first point. When I say vectorization, I mean that you turn the point into a vector with the same coordinates, plus t times x1, y1, z1. It's a very good idea to know this formula. And of course, if you apply this formula, you will get right away the answer, which is 1 minus t times the vector 1, 2, -1, plus t times the vector 3, 1, 3. And that's pretty much it. Okay, I mean, you can, if you want, you can write this as one vector. You can work it out, in other words. But it doesn't mean that you really have to, you don't need to make this. So here you will have minus t plus 3t, so that's plus t, and then you will have 2 minus 2t plus t is minus t, and finally you will have -1 t plus 3t is plus 4t. Something along these lines. I hope I'm not making any numerical error here. There could be some numerical error, so please redo the operations for every simple thing. But the point is that I could have stopped right here, and that would have been a perfectly acceptable parametric equation. The next problem is to find the equation. Again, it's better to say find an equation, not the equation, because there are more than one. An equation for the plane that contains the points one, two, 4. Let's call this A to make our life easier. B, so B is 1, -1, 1. We introduce the notation B. We denote that point by B, and finally the point C. And the reason that we do this is because we know that in order to find the equation of a plane, we need to know 2 things. We need to know a point on the plane and a normal vector, right? So we know that if the normal vector is ABC and the point is x0, y0, z0, then the equation of the plane is A times x minus x0 plus B times y minus y0 plus C times z minus z0 is equal to 0. Don't forget any of those things. Now, so here we don't have just 1 point, we have 3 points. So we have an abundance of points, and we could use any of these points. So let's say I will use the point A. Okay, but we don't have a normal vector. Now we need to find the normal vector by using this point. So how do we do that? The idea is simple. Let me draw a little picture. So imagine that this is your plane that contains the points A, B, and C. So what you do is you can take the vectors AB and AC and pretty much take their cross product. And the cross product is going to be perpendicular to the plane, is going to play the role of the normal vector that we wish to have in this case. So let's do that. Okay, so what is AB cross AC? We need to find the vectors first. And how do we find the vectors? We take the differences between the coordinates of the ending point and the starting point. So for AB, for example, it's going to be 1 minus 1, that's also known as 0. Negative 1 minus 2, that's negative 3. And 1 minus 4, that's also negative 3. And how about AC? For AC, we will have 2 minus 1, that's 1. 1 minus 2, that's negative 1. And 1 minus 4, that's negative 3. So here are the two vectors. Let's take their cross product. So we will have I, J, K, 0, negative 3, negative 3, 1, negative 1, negative 3. And what do we get here? So delete first row and first column, take the determinant that remains, and that will give you 9 minus 3, right? Also known as 6. Delete now the first row and the second column. That will give you 3. It's the middle coordinate, so we need an extra negative sign, so that's negative 3. And finally, delete the first row and the third column, and that will give you 3. So that's our normal vector. You can see that you can take any multiple of it. So for example, you can divide everything by 3 and get 2, negative 1, 1. There's no need to do this. Now I have my normal vector. I have my point, as I said before. So I'm ready to write my equation. I'm not even going to try to simplify it at all. You can simplify it, of course, but minus 3 times y minus 2 and plus 3 times z minus 4. And don't forget to say that this is equal to 0. This is an equation that works how a point belongs to the plane if and only if its coordinates satisfy the equation. And conversely, if you have a point whose coordinates satisfy the equation, then it belongs to the plane. I think I said if and only, but obviously it goes both ways. Okay, let's go to the next problem, which says find all unit vectors that are perpendicular to the plane z equals to 2x minus 3y plus 1. What's the idea here? The idea is that if you have the equation of a plane, you can actually do sort of, I should call it reverse engineering, and find a vector which is perpendicular, which is normal to that plane. To do that, actually, I forgot to write the statement. So, to keep things tidy, let me write the statement of the problem. So that's problem number 3. And we want to find, oops, Zoom is playing some games to me. It's because maybe I'm touching things I shouldn't be touching. But in any case, find all unit vectors that are perpendicular to the plane z is equal to 2x minus 3y plus 1. Okay, so in order to find first of all a perpendicular vector, you can do reverse engineering to the equation of the plane. So by this, what do I mean? Bring everything to the left, to the right-hand side. So 2x minus 3y minus z plus 1 is equal to 0. And then read the coefficients of x, y, and z. So that will give you the vector 2, negative 3, negative 1. And if you look at how these equations get produced, you will understand that the coefficients of x and y and z, when those are on the same side, actually form a vector which is normal to the plane. So this vector is normal to the plane. Yes, but we want these vectors to be unit. What does it mean to be unit? To have length 1. If you have a vector, how do you find a unit vector? And the answer is you need to divide by the magnitude of the vector. And what is the magnitude of the vector 2, negative 3, negative 1? It will be square root of 2 squared, also known as 4, plus negative 3 squared, also known as 9, plus negative 1 squared, which is 1, and that's square root of 14. Okay, so if we put everything together, we get that the A unit vector, which is perpendicular to the plane, is 2 over square root of 14 minus 3 over square root of 14 and negative 1 over square root of 14. Is this the only vector? I mean, let's draw a picture. And there's something obvious here. So if you have one unit vector here, then the opposite vector is also a unit vector, which is also perpendicular. That's why your answer will be complete if you say that this is plus or minus this vector. And that's it. And let's go to the last problem. Let's go to the last problem, and we have problem number 4. And it says to find the intersection of the planes. So find the intersection. The intersection of two intersecting planes is a line. So we're looking for the vector equation of the line. So find the intersection of the planes x plus y plus z is equal to 2, and x plus 2y minus z is equal to 1. Now, so let me draw a picture. If you have two planes that intersect, then the generic picture for two such planes is something like this. Okay, so here are the two planes, and here's this line. We're looking for the equation of this line. And to find the equation of a line, what we could do is find the equation, find 2 points that belong to this line. Okay, so how do we find 2 points that belong to this line? We have these two equations that define the planes. We need to find the coordinates of points that satisfy both equations, 2 of them. But here's the thing. We can certainly do this, but there's a beautiful remark that we can have here. And the remark is that if you actually take the normal vectors to these planes, then the cross product of these normal vectors is actually parallel to the intersection. This beautiful remark allows us to find a vector which is parallel to the intersection by taking what? The cross product of the vectors that are normal to this plane. So for the first plane, I'm reading the coefficients. So that's 1, 1, 1. For the second plane, I'm also reading the coefficients. That's 1, 2, negative 1. I take the cross product, I, j, k. And then I have 1, 1, 1, 1, 2, negative 1. What is this vector? So delete first row, first column. That will give you negative 1 minus 2, that's negative 3. Delete first row, second column. That will give you minus 1 is negative 2, but it's the middle coordinate, so that will be 2. Delete the first row and the third column, that will give you 1. Okay, and now you need just 1 point. So how do you find a point? That's actually kind of fun. So let's do this too. What you need to do is take the equations of the planes. And in general, when you have 2 equations with 3 unknowns, there will be infinitely many solutions. In general, I mean, there could be none. Well, you cannot have just one, but it will be either none or infinitely many. But in any case, the bottom line is that if you have infinitely many solutions, as you do here, to find one, what you can do is take one of the unknowns and set it equal to a number. So let's say, quite arbitrarily, I'm setting z equals 0. Okay, I could set it to be equal to 1, or I could set any of the other 2 variables. But if I do so, I'm getting the system x plus y is equal to 2, x plus 2y is equal to 1, which is pretty simple to solve. If you actually subtract the first equation from the second, you will get y is equal to negative 1. Once you know that y is equal to negative 1, the first equation gives you that x is equal to 3. And pretty much you get the point 3, negative 1, 0. Okay, I think we're done here because we have a point that belongs to the line, meaning the intersection of the 2 planes. We have a vector, and all we need to do is write down the vector equation or a vector equation for the line that goes through the point 3, -1, 0. So I vectorize this point. You won't find this word in a dictionary. And then you add to it t times -3, 2, 1, which is the standard way of producing the equation of a line. If you want, you can also rewrite this as 3 3 minus 3t and -1 plus 2t and t. And that's the equation of your line. And it's actually kind of interesting that this was the only problem where we encountered the basic equation of a line this way. And that completes pretty much all of the problems that you can find on the worksheet for this week. And that concludes our session. Thanks for watching.